Thank you all for joining this session of Shadow the Scientist. My name is Jamika Marshall, and I am very pleased to serve as the Shadow the Scientist Programs Manager. The Shadow the Scientist initiative is offered by a fantastic team at the University of California at Santa Cruz. Now, in this session, we have the privilege of shadowing members of the Gemini North Observing Team, which tonight includes Sonny Stewart and Mark Rawlings. The International Gemini Observatory consists of twin 8.1-meter optical infrared telescopes located on two of the best observing sites on the planet. The Gemini North Telescope is located on Hawaii's Maunakea and is part of an international community of observatories. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership are able to explore the universe in unprecedented depth and detail. Now, tonight, in this session, of course, the observations are taking place behind me in the Hilo Base facility, which houses the Gemini North Control Room. Now, in addition to shadowing the observing team, this session will also feature special Journey Through the Universe themed activities and interactive discussions. And we'll learn more about the Journey Through the Universe program a little bit later in the session. Now, we have several stellar science hosts with us. So let's go over to Brian Lameau, staff scientist here at the Gemini Observatory North, to get us started. Aloha and welcome, Brian.
Aloha, Jamika. How's it going?
Oh, it's going well, going well. We're excited to be here with you all tonight.
So hi everybody. I'm Brian Lameau. This is Emily Peavy next to me.
Aloha, everyone.
And we are here in the Hilo Base facility with Jamika and with Mark and with Sunny. And we're very much hoping to get some astronomical photons tonight. So we are in Hilo on the east side of the Big Island. We're about 40 kilometers away from Maunakea. We're operating the telescope remotely from here. Mark and Sunny are doing that. We have just had sunset about an hour ago, roughly. And so normally this would be the time when we would just be getting set up on sky. We would be taking our beginning of the night calibrations, calibrating our mirror, calibrating our telescope, calibrating our instruments, and getting ready to do science for the night. So this time of year, we observe from about 7 o'clock p.m., which is 7:15 right now, all the way until, depending on the types of observations, could be up till about 6:30 or 7 in the morning. And so it's a long night for our observers, tonight for Mark and for Sunny. Unfortunately, tonight, so hold on a sec.
We're going to show you a view of our live cameras at the summit of the mountain.
So let me share the screen. Okay, I see. Everybody can see that. So so we're at the Hilo Base facility. So as I said, we're about 40 kilometers away from the summit of Mauna Kea. In fact, Gemini North and Gemini South, our sister telescope in the south in Chile, they're both there's nobody at the telescope at nighttime. So everything we do from the Hilo Base facility. And in order to do that, we have to have a ton of different monitors, sensors, cameras to be able to see what the conditions up on Mauna Kea are, to be able to see that our instruments are within the required parameters, that our telescope is within the required parameters. And so there are, I guess, near 1,000 sensors on the telescope and on the dome structure. There's roughly 20 to 40 sensors in each one of our instruments. And all this data is being monitored at nighttime, in this case by Sunny and by Mark. And so what they're seeing here, these are our very light sensitive cameras that are mounted on our dome structure. And we have one pointing, so Gemini North is on the east ridge of Maunakea. So Hilo is actually over here underneath the clouds as usual. And as usual in February anyways. And so Hilo's underneath the clouds, and this is looking over the east ledge of Maunakea. This is looking to the south. This is looking to the north. So this is the Keck 2 telescope and the NASA Infrared Telescope facility. And then the up-facing cam, so looking directly up towards zenith.
Yeah.
And in addition, you see all these other things on the side. So these aren't just, fun pictures. These are really useful information for astronomers to be able to gauge the conditions. So we have wind speed, wind direction, the relative humidity, some satellite images, some infrared water vapor images, and then over here are a bunch of graphs that allow us to measure various parameters. And so the observers, Sunny and Mark, are taking a look at this, and what they see is the threat of some clouds that may carry precipitation with them. And so out of abundance of caution right now, we're actually staying closed. We did do some night work where we were slewing the telescope and taking some spectra, which we can talk about later, but just with the dome structure closed. And so we're actually in a holding pattern right now. It could be that we could open up at any time, but we are very, very careful with our telescope and our instruments, because if there's any precipitation, any chance of damage, we want to be using these telescopes every single night as much as we possibly can. And so we try to be really, really careful. So that's where we are right now, but you can see Maunakea is beautiful anyways.
Yeah.
The snow's there. Poliahu visited not too long ago, really for the first time this winter.
But we've had a very, very dry and hot winter, and you can really see with the camera, it's just like a big contrast of like the snow on it. Can you scroll down to the north facing camera? Just because I think a second ago you were looking at that camera and you're like breaking down some of these clouds and some of the things that you were seeing. Would you mind sharing that?
Yeah, so we have Kilauea going off right now. That's one of the most active volcanoes in the world. And it's not a threat to Hilo, but it does output a lot of gas and sulfur dioxide in particular. And this is something, I was actually over on the other side of the island with my family earlier today, and we could really tell it's basically like a thick fog that you're walking through or that you're driving through, and on the island they call it fog. But we can measure this in our particulate sensors up on the summit. And maybe I'll ask Sunny if it looks like that there's more particulates later. But I'm guessing that we see some effect of that, and we usually do. This was also the case when Mauna Loa, which is the world's biggest volcano, was going off about 2 years ago. There was a lot of SO2, and it really, the combination of humidity and SO2 is not good. It basically causes acid rain. So that's very bad for our instruments. So we have to, monitor that. We have to monitor the humidity. So, these clouds are, the relative humidity right now is only 20% or so. Yeah, 21%. But these clouds can contain precipitation, and it can happen really fast. And so our dome can close fast. We're one of the fastest telescopes up on Mauna Kea, but, still not that fast. So
Yeah.
I've been open before when we were at the edge. And you want to push it, but you don't want to push it too hard. So that's where we are tonight.
I'll also point out in your up-facing camera, so that's the one that's at the summit and facing zenith. But we got a lot of clouds, not like too many clouds in order for us to open, but I can see the bottom half of the constellation of Orion peeking out with those clouds chasing by. I'm not sure if anyone can see that.
Yeah, so let's see. I guess you guys can see my cursor. So
yeah,
Emily's pointing to right here. So you can see the belt of Orion. You can see, I guess it's Rigel there, right? And maybe Bellatrix, and then the sword. Yeah.
Yeah, and you can just imagine, like, if those clouds weren't there, just like how clear, like just that zenith sky would be.
Yeah. So it's definitely not. It's not a necessarily bad night. It's a night that there's a lot of hope for something better. But right now, Mauna Kea is really just trying to figure itself out, and this happens a lot right around sunset. And usually the night settles down at some point, either to a night where we just simply can't observe, or to a night that it's absolutely gorgeous. And so the inversion layer pushes all this stuff down. So maybe before we go too much further, we could go to the control room, and Sunny, Mark, you guys want to introduce yourself real quick and talk maybe just a bit about your roles, if you'd be willing?
Yep. Hello, everyone. So I'm Sunny. I'm actually lucky enough to grow up here on the Big Island and continue my sort of, I don't want to say dream, but my passion of astronomy, and here now at Gemini and making a good career of being an astronomer here.
My name's Mark. I'm one of the staff astronomers like Brian here at Gemini. I've actually worked at about 4 or 5 different major telescopes around the world. So I spent some time in Chile and other places. It's great. I've lived in Hawaii for quite a long time now, although I don't sound like a local guy.
Mark, Sunny, will you guys talk about like your individual roles, like just the basic responsibilities that you guys have? Because notice there's 2 people in the room. Is that necessary? Is that like the same for all telescopes?
So we have a number of things going on. First of all, we used to operate at the summit, and for safety reasons, we always had 2 people. And that was convenient because it's a lot of work, and we have our roles divided, as Brian was alluding to. I'm primarily operating the telescope, so I'm doing the technical stuff of slewing the telescope, moving it to new targets. If something goes wrong, I'm going to be troubleshooting it, trying to find out what the problem is, usually rebooting some component of the telescope and trying again. And if things get really, really bad, then I'm the guy who calls for help, and we get the engineers involved. And then I'll let Mark talk about what his primary role is here.
So I'm the shift observer. I'm the astronomer. So I tend to handle the science side of things. So my side of the room, we think about how I look at how the instruments are behaving and making sure that the signal that we're getting through is consistent with what we're expecting, and what sort of science we're going to be doing, which programs we're going to observe next during the night. And so I'm kind of staying on top of the science plans, and maybe interpreting what we're seeing to make sure we can decide whether the data we're getting are scientifically useful or whether we need to maybe adjust something. So I tend to handle the science, and he handles all of the more of the technical side of things. Yeah.
And so, Mark, the things that we're planning on looking at tonight, this is all your science, or this is somebody else's science, or you're doing service work? How's it work?
Yeah, this is mostly other people's science tonight. So we run what we call a queue system. So a lot of astronomers from all over the world, actually, they go through a process where they submit proposals to say, I want to use 5 hours of Gemini time to do this really interesting bit of science, like this galaxy or whatever. And then there's a competitive process, and these are all reviewed and checked for technical feasibility. And the ones that make it through, we turn them into effectively computer programs for the telescope. And so we break them down into chunks of observations, and then we basically throw them onto a big pool inside a computer. And then during the night, we actually select and run pieces of programs based on the relative priority of programs, when the sources are actually observable because they're above the horizon, that sort of thing. And so we try and complete people's programs, but we often do it in a piecewise fashion during the semester. We go through this typically, this review process normally twice a year. But we have larger programs that will span multiple semesters. They may last a couple of years or so.
And Mark's being a little bit modest because he's the person that's in charge of collating, collecting all of these programs from all of our different partner countries and putting them, all this mishmash, together in some sort of coherent order so that we can easily digest it and plan it for each semester. And that process is a long one, a very involved one, and one that has many participants from many different countries.
Yeah, we have, I sort of chair a group of people at different, so we have representatives from all of our partner regions. So that includes Canada and Chile and University of Hawaii and Argentina and Brazil and South Korea. And we also share some time with folks that our friends at the Subaru Telescope. That's Japanese, and so we have to kind of rationalize through all of these various options and make sure everybody gets what they've asked for and make sure that everybody's happy. So it is kind of a lot of work. Yeah. Thank you, Brian.
But you've just stepped down from that, so you can now take a break and do some other fun work that maybe doesn't
Yes.
involve so many emails.
Indeed, yeah. I'm handing this task over to a guy who's actually based out of Gemini South Telescope. So the folks in the south are going to be handling this for a couple of years now. So yeah, so I'm gonna get to do a bit of science and a few other bits and pieces. I'm involved with a bunch of the instruments and various other technical things here. So I'll be working more on those as well.
And can either of you give us like a rundown of what your calculus is for like potentially opening up later, or like what you see in terms of the conditions and the prospects for observing later? It seems like, at least, yeah, in the up-facing cam, serious, but not terrible. But yeah, what are you guys thinking?
Yeah, so that the whether or not we open the telescope is my responsibility. And looking at right now, you're right, it is pretty clear, and this is what astronomers like to call a sucker hole, because in about 10 minutes, the clouds are going to come right back. And we often say, you know, as the word implies, it would be a sucker to open up right now and try and observe. So we're waiting for these clouds to pass. They're really thick, and we just aren't going to get any light passing through them. And given the risk that precipitation could fall out of them, like Mark was saying, we want to prevent our telescope from getting injured or damaged. And that's, again, my responsibility is to keep our hardware safe, keep the staff safe. And that's so we're going to wait until these clouds pass. Looking at the satellite, we're thinking it'll be sometime in the middle of the night, like 11 or midnight-ish. But if they're looking good, we'll open before that.
The general operating principle for major observatories is safety of people first, safety of facilities second, then getting as much science as you can third. So we do want to make sure that the people and the instrumentation is safe. But beyond that, we want to get as much science done as we can.
I see we have. Oh, go on.
Oh, thank you. Sorry, Emily. And then yes, we'll come to a question we have in the chat. So to Sunny, so when you are needing to make that decision about opening, how long do you have to wait before you make that decision to open and then actually opening?
It depends on the conditions. If we have just clouds, we can pretty much instantly make that decision and open up. I've already prepped the telescope, so it will just be about 5 minutes to open the dome, and we can slew somewhere. If conditions are more impactful, like especially if we have fog, because we're remote, we can't go outside and look and get a real immediate sense. So we like to wait about 40 minutes with the conditions being clear before we commit to reopening in that situation.
Perfect. Thank you. And yes, Emily, with our question we have in the chat.
Yeah, so we have a question in the chat of how do we track blue shift and red shift in the nighttime sky? And that is going to really be different based off of the type of object that that you're wanting to detect that with. So for those who might not know, blue shift and red shift refers to when objects in the universe are moving in relation to us. And so I'm going to share my screen, and I'm going to jump around, and a lot of my screen is going to be Google search windows, but just to give perspective of what we're looking at.
I'll just mention that, yeah, so with spectroscopy, so this is a question related to spectroscopy, and we'll be talking about the difference between imaging and spectroscopy a little bit later.
Oh, yes, excellent.
So I'm very happy to talk about how we track the movement of space
Yeah.
rainbows.
So my first screen here, I showed a spectra of a star, which this is really a lot of details here, but I'm just going to jump into this other screen that just shows a very simple spectrum of white light. So if you had a light source that was purely white light, you would be able to just see all of the colors of that light. Now, when we're thinking about blue shift and red shift, we're thinking of an object moving. And when an object moves, the light that we're receiving from that source will end up getting shifted on the light spectrum based off of how it's moving in relation to us. And it works just like the Doppler shift, or that's actually what it's called, the Doppler shift. And it works very similarly to how we experience Doppler with sound. So you can imagine if you're standing still on a highway and there's an ambulance coming towards you. As the ambulance is coming close to you, the siren is sounding very high-pitched. And then once it passes you, the sound of the siren gets lower pitched as it's going away. And that's the Doppler shift with sound. We also experience that Doppler shift with light because light does travel in waves. So when there's a light source that is moving closer to us, then the wave of the light gets shortened a little bit and the light becomes blue shifted. And when it's going farther away from us, then it becomes red shifted. And so how we're detecting that with a telescope, it is, like I said, it is going to very much change based off of what you're looking at, what type of observation you're wanting to make. If you're looking at something that's really, really big, like a galaxy, then you are usually for galaxies, we're seeing them be red shifted, and that is proof of our universe expanding because all galaxies we look at, we see the light getting stretched out and moving farther away from us. A star we're going to be tracking whether or not that star is moving closer to us or moving farther away from us. But one of those things that we track, if we look here in this spectra of stars that I just Googled, but you can see that when we look at a star spectra, we are seeing these little lines dipping down, and those are emission lines. There is something that is absorbing light. It's usually related to one element, and we typically know where that element is going to land on where the wavelength, and we'll see if that element is off of where it is landing on that wavelength to determine if the star is blue shifted, meaning it's moving towards us, or red shifted, and it's moving away from us. Now,
And so in this in this particular example, so there's a quantity down at the bottom. So this is likely an A star. So this is a star that's a little bit more massive, a little bit brighter than our sun.
mhm.
So just a little bit, about 1.5 times hotter, some few times brighter. And so you can tell that by this. So these features that Emily was referring to, these absorption features in the black line, these all come from hydrogen. So you can see the green line on the second from the right. It says H alpha right at the top there. And then there's H gamma over there, H beta, H delta. And so we recognize this from a laboratory experiment, and then we match it up, and then we find out the redshift and blue shift, as Emily said. And so there's this quantity right at the bottom that says Z equals 0.0005, and then some uncertainty on that measurement. And then it says star. So it's been determined as a star. And so that Z measurement is actually called redshift. It's our shorthand for redshift in astronomy. We use Z for other things, but normally redshift. And very roughly, that can be thought of as the recession velocity. So it is redshifted, if it's positive, the recession velocity divided by the speed of light. So this is 0.05% of the speed of light. That's what it's receiving at. So the speed of light is quite fast. So even 0.05% is still quite fast.
And we can use redshift for a lot of things. So the first thing that my brain always jumps to with redshift, because the first thing I learned it for was for redshifted galaxies. And that was around the turn of the century when we're really figuring out galaxies and we're really figuring what's going on with the universe. Is the universe stable? Is it contracting or is it expanding? Many people thought that the universe was stable, that nothing was really changing in the universe. And if the universe was stable, we would expect that about half the galaxies would be moving towards us and about half galaxies would be moving away from us. And so, but we didn't find that. We found that 90% of galaxies are all moving away from us. And that is the evidence that led to the expansion of the universe. Another great way that redshift and blueshift are often used with stars is we can also detect exoplanets moving around stars, and we watch. We won't see the planet itself, but we'll see the star.
Sometimes we do.
Sometimes we do.
From Gemini Observatory,
Sometimes we do. Oh yes, you're absolutely right. But in terms for this experiment,
first place on the planet that we saw.
I can get that picture.
Yeah. I have it in my presentation actually.
Oh, okay,
Yeah,
okay, and then I will skip for that.
But I also have a good video of the Doppler shift on a exoplanet system.
Oh, wonderful. Yeah. But yeah, as the star while the planet's orbiting the star, the planet's gravity will cause the star to wibble wobble, and we'll detect that as the Doppler shift of blue shift and red shift. And then that's how you can discover a planet orbiting around another star.
Yep.
I'm going to go ahead and stop sharing here. And I'll say really the spectra that we're looking at is just an absolutely random spectra that I just Googled star spectra. And I was like, oh, okay, this will be an example.
There's a lot of A stars in the universe.
Yeah.
So it's not terribly unrepresentative.
Yeah.
So I see there's another question in the chat. Maybe before we get to Alani's question, we could go over Journey Through the Universe this week, and then maybe we could ask y'all some questions, and then we could come back to Alani's question, because we were actually just taking calibrations right before we started the session. So I'm very happy to talk about that. But let's get oriented just a little bit before we do that.
Yeah, everyone. And this is very much my presentation style of just like talking once we have questions and just going from that.
Okay.
I'm just going to share a slide here relating to Journey Through the Universe. So our regular Shadow the Scientist sessions, we love working with Shadow the Scientist. And here in Hawaii with the Gemini North Telescope and with many other organizations across the Hawaii Island, we are just finishing up our week of Journey Through the Universe. This is an annual program that is just finished its 21st year of operations here on Hawaii Island. Through this program, professionals working with the observatories, NASA, science institutions, all working in the STEM field. We have people that are scientists, we have people that are engineers, we have people that are just great communicators, all go to visit the Hawaii Department of Education schools across the Hilo Waikea district and share their knowledge with presentations and career panels and experiments throughout the entire week. So closing out this week, we had 60-some STEM professionals visiting over 300 classrooms and servicing more than 3,700 students across the Hilo complex. And in this slide, you can just see, this is actually, most of these pictures are from last year, but since we're still processing our pictures from this year, since the week only just finished, you can see a lot of interactive engagement with our students. And I want to give a shout out to one person in particular, but one person who's also representing a group of people. And on our screen, I have my mouse circling Wataru Hayashi, who is a grad student at the University of California. He is working on his PhD studying fusion physics and really getting into experimentations of figuring out how to have fusion be an energy source for our future. And specifically, Wataru Hayashi, he graduated from Waikea High School, which is one of our local high schools here in Hilo. And he comes back every year in order to help out with Journey Through the Universe. And this year, he even also helped recruit some of his high school classmates as well. So we had 3 representatives specifically from Waikea High and from the year that he graduated. And he pointed out to me, it's like we had, so it was Wataru Hayashi, it was Logan Sato, Hannah Blue. We had other graduates from Waikea High and Hilo High as well coming through. I will say though, Wataru, he was talking with me and he was like, hey, did you realize that the 3 of us were all same graduating class? I was like, awesome, that's really amazing. And I asked him what year did he graduate high school? And he said 2016. And I was like, I
Oops.
wasn't quite prepped for that one, but it was so wonderful that he was able to come back and share all of this amazing knowledge with our students and help keep this program going forward and helping our students feel like they have a future here in Hawaii Island in STEM in the world.
Yeah, and I'll just say, I mean, these pictures here aren't just like cherry picked. Like this is the real, but like when we go into classrooms, this is what it's really like. And the students absolutely love us being there. We love to be there. And there's just so much energy and so much enthusiasm for the activities that we do and just for astronomy in general. So it's really a pleasure to be involved with.
It's heartwarming just like talking with students and just seeing what they're interested in and being able to tackle their questions.
Yeah. Yeah, the curiosity is absolutely wonderful. So speaking of curiosity, thanks, Emily.
Yeah.
So we had a few questions for everybody. This is not the normal way that we do Shadow the Scientist, but since we're doing our special journey edition, our interactive edition, we had a few questions for people, and I think we have a poll set up just to kind of get us oriented in where we are and you know what are the capabilities of the telescope that we're using and the site that we're on.
It is not graded.
It's not graded.
However, we do want you to think about some of the things with Shadow the Scientist. I'm going to go ahead and read out the questions. So question number 1, when you look up at the night sky, what fraction of the stars do you see are inside our own Milky Way? And then our potential answers are none of them, about 10%, about half of them, all of them, and then what stars? I'm in Hilo. I'm in a place with light pollution. We don't even see that. Hilo's
And a
actually
lot
not
of
that.
clouds. Yeah, Hilo's not that bad.
Hilo's not as bad for light pollution,
But,
honestly. Yeah, we just have to
one of the
battle
wettest
clouds.
places on Earth. So
Yep.
yeah, nighttime, and it usually comes at night, so not great for the viewing. Got to drive a little ways to get there.
And then question number 2, and I actually don't know this question off the top of my head. How many times fainter can the Gemini North Telescope see than the human eye? So 5 times fainter, so that means that if your human eye sees 1 star, Gemini would see 5 stars. 1,000 times fainter, 1,000,000 times fainter, 1,000 million times fainter, or 1 billion. About the same. I don't like to brag, but I have good eye vision.
So guys, feel free to, on the I guess the poll popped up, and so feel free to answer these whatever
Oh yeah, we got
whatever
some answers
draws you.
coming in. Yeah, let's see. Okay. And then question number 3. I'm just going to read them out. If you're still working on one of the previous questions, I'm not rushing, just making sure that we're all able to hear. What is the most scientifically productive astronomical observing site on the planet? Cerro Paranal in Chile, which is the site for VLT and VISTA. Cerro Patron, Chile, which is the site for the Gemini South Telescope, so our twin, as well as Rubin, which is about to see first light for coming up pretty soon, and SOAR. Haleakala, Maui, Falk's Telescope, and the Daniel K. Inouye Solar Telescope. Maunakea, Hawaii, represented.
Yep.
And that is Gemini North, Keck, CFHT, Subaru, IRTF, JCMT, student observatories, all of what many fantastic observatory sites. And then Apache Point, which is in New Mexico. That's the site for the Astronomical Research Consortium telescopes and Sloan Foundation Telescope.
So
And
if anybody's heard of the Sloan Digital Sky Survey, which is a very, very important survey for humanity in general, but for the astronomical community, it's where a lot of our knowledge of the let's say local-ish universe comes from and how we calibrate out to further distances.
Yeah.
So that's a really important one.
these are data, yeah. And then
Not that the others aren't.
No, yeah.
Put it in point.
Kip Peak, Arizona, and it's home of the largest arrays of optical and optical and radio telescopes in the world, including Nicolas del Mayual 4-meter telescope and the WIN 3.5-meter telescope. And so once again, that question was most scientifically productive astronomical observing site on the planet.
So yeah, I think in this particular case, so you have to have a metric. Always in science, we have to have a metric. So what constitutes scientifically productive? Okay, so you guys ready for what scientifically productive is by the particular study that I cross-referenced here? So this is you take all the professional journal articles and you average out the number of so astronomical journal articles, and you average out the number of citations. So this is the currency of an astronomer is citations. It says, oh wow, you did that? Okay. All right, that's a good idea. So I'm gonna build off of that idea. So that's a citation. It's like, hey, you did a good job, and I wanna build off of that. Sometimes it's like, hey, you did a really bad job, and I want to point that out. But most of the time, it's like that was a good job. I want to point that out. And so you average all those out, and let's say over the course of 1 year, Mark writes a paper, and 5 people say, "Hey, good job, Mark," and that's a reasonable number. And so then so let's say he used Maunakea, so he used Gemini North Telescope, and then somebody else comes along, let's say another staff scientist, not to be named, Emma Farina, and uses the Very Large Telescope Array and Cerro Paranal. And he writes a paper, and only 2 people say, well, that's a really good idea. Well, so then Mark's paper is more scientifically productive. It's that more scientists said, aha, that's a good idea. And so, yay, Mark wins. And so that means Maunakea wins in that, because we're not selfish. So Maunakea wins. And so we do this over all the papers. So in this particular study, this is done over all the papers, and they source which sites. So a lot of times we use multiple sites, but which sites were used for that study. And so then they just average all of those across a given site relative to the average across all journals. And that is scientifically productive. That's what we consider scientifically productive. So that means if you have more telescopes, that's important. And that means if you have more productive telescopes, you have telescopes that both can see like deeper, but also that they see like a broad breadth of different types of science, because of course it's important to diversify, and there's lots of different types of astrophysics.
Thank you for explaining that, what was scientifically productive means, because I was kind of up in the air about how come to that conclusion, but that makes a lot of sense.
It's really contorted, but I just wanted to show that these studies are, they're only as good as their operational definitions, honestly, most science. But you make a definition, you say, okay, in the context of that definition, here we're gonna grade these things, and it's not uncommon. Like I write papers where I look at a lot of different clusters of galaxies and I rank them in some way, and I try to cross-correlate that with other physical properties of clusters as measured by other people or by myself, and then we interrelate those variables. And then we say, aha, this variable correlates with this variable. That means such and such. And so always defining a metric is important. What are you calculating in order to interpret what you're actually seeing? So this is not just, it's made up in the beginning, but it's made up based off of like some fact that we can point to. So this is not, in this particular case, it's not physics. It's some combination of sociology and social factors and science and lots of other things. But so maybe we can start with the first question.
Would you guys mind if I do like a little presentation for the first question?
No, not at all.
Okay.
That'd be awesome.
All right. I'm gonna just minimize that. I'm gonna share screen and use a program called Worldwide Telescope. And should I can see it? I did not share screen. Share. There. Okay. Okay, excellent.
Does it end up being behind the pole?
Is it? Oh, it's behind the pole. Maybe. Maybe can we end the poll?
Oh, we can see it.
Oh, you guys can see it? Okay. From our perspective in here, it's behind the poll. I can use my.
Okay.
If you've answered,
No
if you've answered
worries.
the question, probably, right?
I'll also
Oh.
end the poll too, so no worries. I'll end the poll, but yes.
All right. So this is a completely free program that you can download onto your own computer. You can also use it for in a web server as well, but this is a program called Worldwide Telescope put together by the American Astronomical Society. And actually, one of the things that I was looking at here before we logged on is there is a collection of Gemini studies where you can explore objects that were imaged with the Gemini observatories. This is very, very famous image that we call the fireworks galaxy. It's often in our building here. It's a really beautiful spiral galaxy.
The picture, not the galaxy.
Oh, the picture,
Yeah,
yeah, it
okay,
was,
but not the galaxy.
yeah.
Thankfully.
That we don't have the galaxy in the building. I wish. I love galaxies. But we're going to get some perspective of just how big a galaxy is. And so for that, we're going to jump over to looking at our solar system. And we're going to start on Earth. It's in our own solar system. And we're going to just see how big the universe is and where all the stars in our night sky are in relation to the universe. But I always want to start with here's the Earth. And this is more or less real time. So just after sunset in Hawaii, you can see the Terminator there. And I always want to zoom in on where we are. So observatory on Gemini North Observatory is at the summit of Maunakea here. And then we are sitting just north of the university in Hilo. Right there.
There we are. Wave.
Yep. The image isn't quite live. You can see this picture was taken during daytime. So, but we can't, so I don't think my car's in the parking lot there. But giving us perspective of just where we are on the planet Earth. And then backing out from the planet Earth, you can try to keep an eye on ourselves sitting there at Hilo Base Facility on the island of Hawaii, the Hawaiian island chain, in the middle of the Pacific Ocean, our planet Earth. And we go a bit farther out, we can see the orbit of our moon, the orbit of the rest of the planets of our solar system. And as we're flying through space, you can start to see some of the stars that would typically decorate our nighttime sky in the background. In the back here, we can see the shape of Maui's fishhook. And then the image that Worldwide Telescope is using of the Milky Way is an infrared image, but you can see that kind of reddish glow in the back there. That's the central region of the Milky Way. But right now we're going to go where no man has gone before. We have already left the galaxy, or excuse me, oh my gosh, we've already left the solar system. Not quite the galaxy yet. We've just left the solar system. So we're already beyond where the Voyager missions have gone, and we made the sun a little bit bigger, so it was a bit easier for us to see in our dot there. But for as long as you can, try to keep an eye on yourself sitting there on that planet Earth, orbiting around the sun. And as we back away, you guys can start to see the stars that were making up some of our recognized images are now starting to kind of stretch in different areas. And right around here, this, you can imagine a sphere of stars just around the distance that we are currently at, that would be more or less every single star that you can see in the nighttime sky. On the clearest, darkest, best night of observing, our human eyes can see at most around 6,000 stars in the sky. And all of those stars are just one small portion of the Milky Way galaxy. This is a great model of the Milky Way galaxy. We estimate that the Milky Way galaxy contains around 200 billion stars. Whenever we're talking about this, I always want to pause and take a moment and put some big numbers into context, because it's really easy for our brains to just completely lose track of how big a big number is. For a million, if you're thinking about numbers in terms of seconds, so 60 seconds in a minute, etc., 1 million seconds is about 12 days. So a week and a half is about 1,000,000 seconds. Maybe the average time of your average vacation is about 1,000,000 seconds. For a billion with a B, 1 billion seconds is 32 years. So the human eye can see around 6,000 stars. Inside the Milky Way, there's around 200 billion stars. That's so many stars that if you wanted to count every star and you counted one star a second, you never stopped, it would take you around 6,400 years.
And by converse, if you counted the number of stars that you could see naked eye, best night ever, naked eye, it would be about an hour, 1 per second, hour, 45 minutes.
There you go.
Yeah,
See?
you can get it done. Like you can get it done before dinner.
That was much better math than I was about to
Yeah.
do on the top of my head. I was like, wait, I thought you were about to ask me. I was like, oh, wait, no. I don't know that one.
No, that's just like a aperitivo. You can get it done.
There we
right?
go, yeah. And that's why we want telescopes. So the first question was, how many stars, of the stars that you can see out in the night sky, how many of them are within the Milky Way galaxy? And the answer is all of them. If you wanted to get really, really technical with me, there is the Andromeda galaxy, which you can see with the naked eye, which is a collection of stars that would be outside of the Milky Way. But that's if you're getting technical. If we're talking only individual stars that you can see their individual points, every single individual point star that you see is another star of the Milky Way. I always like to say that the Milky Way is like a giant pancake, and you can even see with this model of the Milky Way, it's very pancakey shaped. If the Milky Way is a pancake, then all the stars are the pieces of flour that build up the pancake. So the sun is one piece of flour about an inch from the edge of your pancake. When next time you're eating breakfast, just picture that. And then all the other stars that make up your nighttime sky are just the other pieces of flour in our giant cosmic pancake.
Thank you, Emily.
Yeah.
So for the person that answered about half of them, if you answered about half of them because you were getting technical and going for Andromeda, Andromeda is roughly the same size as Milky Way, a little bit bigger, a little fewer more stars, but if you answered for that reason, then okay, because with the with the telescope you can see a few individual stars. With even just like a kind of 8-inch telescope, you can see a few stars on the outskirts of Andromeda. With an 8-meter telescope or a 10-meter telescope, you can actually see individual stars in Andromeda, which some of the scientists that are running Shadow the Scientist sessions, this is something that they do. So taking spectroscopy of individual stars in Andromeda or satellite galaxies around Andromeda.
Someone in the chat was also being technical with me and the large and small Magellanic Clouds.
And the Magellanic Clouds as well, yeah.
I will say there are some
We can't see them here.
astronomers.
You can't see them here.
You can
Well,
see-
you could see just the beginning, right? Like
No one can see them. In Hawaii, yeah.
yeah.
You don't have to be South Point for it, but you can see them.
South Point, right? Yeah.
Yeah,
So we see it like a certain time of year. We can just see it pop over the horizon. Right?
Yeah.
Yeah.
We don't actually have large.
Yeah.
You can. I've seen them very well from South Point. I think from Mauna Kea is a bit harder because Mauna Loa gets in the way.
Yeah. You have
But,
to be right place, right time.
But in
for sure.
Hawaii, if you're saying like if you're not at Gemini Telescope, if you're not using Gemini Telescope to observe it, you can see them pretty well. But I was going to say there are some astronomers that will argue with you that the large and small Magellanic Clouds are part of the Milky Way because they are in the Milky Way's halo. They're about to get eaten by the Milky Way. And when I say about, I mean in a few million years, but in cosmic time, they're about to get eaten by the Milky Way. So I'll take that technicality and I'll raise you another one.
Right. Operational definitions matter, right?
Yep.
But I would say a lot of astronomers would say the opposite. So then there could be a
Yeah.
healthy debate. So in any case, there are several right answers here, but probably the most right is all of them. So thank you very much for that, Emily. So the second question we had was about how many times fainter the Gemini North Telescope can see than the human eye. So Emily mentioned that you can see about 6,000 stars on a really, really good night. So if you're up on Mauna Kea and you're not oxygen deprived, so maybe you have some other way of getting oxygen, and you look up, it's a clear night. Perhaps you'd see, you know, in the several thousands of stars. In astronomy, we have a system called magnitudes. It's a very, very silly system and very complicated system, but it's the way that we measure brightness, like just kind of initially anyways. And then we convert that into units that actually make sense, kind of. And so the magnitude system is a logarithmic system. And so for every 2.5 magnitudes, so if you change 2.5 magnitudes, and in fact, if you increase 2.5 magnitudes, you decrease in brightness a factor of 10. So if you look at something that's a magnitude 2.5 star, that would be a pretty bright star. That's one that you can fairly easily see naked eye on a clear night. And then you looked at a 5th magnitude star, so you're 2.5 away from 2.5. That's a factor of 10 less bright. And the limit of human vision, depending on how good your eyes are, is roughly about 5 or 6 magnitudes. So 6.5 if you're really, really good and you see a you know, very dark sky. And so that's the 6,000 stars or so that you can see. Those are all brighter than about 6 or 6.5 magnitudes. The Gemini North Telescope, on the other hand, can see to about 26.5 magnitudes. So if we have, we take an image, we can actually, you know, honestly, we've gotten, okay, I may have lowballed this here. So I was actually surprised that a program that we had recently, so if we take an image and we do that for about 2 or 3 hours, we can get down to about 28.5 magnitudes. So a little bit fainter than my estimate. But so if we take 6.5 and 26.5, that's 20 magnitudes. So that's 8 2.5s. So that would be 10 to the 8. So that's 100 million. And so so then if we go to 28th, 29th magnitude, that's already a billion. So it's a billion times. So we can see things a billion times fainter with the Gemini North Telescope on a clear night than we can with the human eye.
That's amazing.
So that's the advantage of having 8.1 meters of glass reflecting the light. So it's a really, really big eye. And the light collecting power goes as the size, the aperture, the diameter of the primary mirror squared, modulo the holes that we put in the mirror for the secondary and other optics. And so this is a huge increase. You know, you have your relatively small eye, you have this huge piece of glass, which is the primary mirror of the telescope, and that is all amplified by a squared factor. So you multiply by itself. So about 1,000 times, a million times fainter, a billion, that's the right answer. Okay, and then the last question that we had was about what is the most scientifically productive astronomical site on Earth? There was Cerro Paranal, where the VLT and Vista telescopes are, Cerro Pachon, where Gemini South, Reuben is coming on shortly, and SOAR, Haleakala, Mauna Kea, Apache Point, and Kitt Peak. Let's see, I'll actually... Jamaica, do you have the graphic handy somewhere? Otherwise, I can share it on a different screen.
I could share it.
Oh, go ahead. Yeah, go ahead, Emily.
Okay.
I'll just move it off into its own.
Oh, okay. All right. And we promise we're not biased. You're just it's actually good that Brian shared the explanation of this data of not just why of how this measure is being collected, sort of thing. We're not just tooting our own. We're not making up stuff to make us sound good. This is accurate.
Yeah. So it turns out Mauna Kea is the most productive site on Earth. It's not even really close. And so you can see Cerro Paranal, which is where VLT, it's mostly VLT, honestly. So the VLT is 3 8.2 meter telescopes. So, or sorry, 4. So 4 times Gemini, basically, all in one site, and they all have different instruments. So I mentioned earlier that breadth is important. All these different instruments do different things. They have 4 operating telescopes, all the size of Gemini. They can be used individually, they can be used collectively. And so a very versatile system of telescopes. And still, Maunakea, with all of its observatories, roughly 2 times more productive than Cerro Paranal. And again, we work in conjunction with Cerro Paranal. So a lot of the astronomers here use both Cerro Paranal and Maunakea telescopes. In fact, all of these sites, ALMA is one that I know Mark uses quite a bit, and I use to look at distant galaxies. He looks closer by. But you can see Apache Point Observatory in 3rd place there. In fact, a lot of the work that we do on Maunakea and with these big telescopes relies a lot on the foundational work that Apache Point did, so that we could calibrate the things. It takes us less time to calibrate the things that we need to calibrate in order to understand what type of information we're getting from the distant universe. So in the studies that I do, where I look at very distant galaxies, we would cross-correlate with observations from Apache Point. We would understand, okay, if we look up at the sky for 1 hour, then we see things in the foreground. We take an image and we see some things in the foreground, because I'm primarily interested in things in the background. We see some bright stuff in the foreground. We say, oh, what did they see over in Apache Point? Well, how bright were those things when they observed them? If it's galaxies and stars, they usually don't change brightness on very short time scales. Galaxies especially, except modulo supernovae. And so we can actually calibrate those images using the Apache Point data. And this is very powerful because they've looked at a very large portion of the northern hemisphere. So so this isn't a competition, kind of. Just if it were, we would win. But it is to say that everybody's productivity is dependent on everybody else's productivity. And the astronomical community is very interconnected in terms of the instrumentation, in terms of the sites. I mean, Mark mentioned that he worked on 4 or 5 other telescopes. And so he brings all that expertise to bear here at Gemini. And so we work together on developing concepts, on developing observing models, on, as Mark said, we share time with the Subaru Observatory. They share time with us. I was observing on Subaru quite a bit this past semester. And so we're all interlinked, and we all have our own specialties and our own capabilities.
All right, guys. So how did you do on our quiz?
Yeah, how did it go?
I'm not sure if I can see the results.
Oh, I shared the results, but you know what? I can't actually see the results. I shared them.
Oh. I can see them on our big screen, but I can't see it.
Let's see. Go back.
Okay.
There we go. That's
Oh,
2
I
of
see.
3. So I'll go to 1 of 3.
Okay, question number 1. 40% got the correct answer of all of them, but we have a good spread. And I also will accept bias of if you can't even see your stars, then then they're like Schrodinger's cat. They're all in the Milky Way, and none of them are in the Milky Way if you can't see any of them.
And most of it's just a street light, anyways.
Yep. Okay, and then our second spread question for how many times fainter can the Gemini North see than the human eye? And I would have had a tough time with this question. And our answer was about 1 billion. And so we had 30%. So that was the second to last answer was the correct one. Okay. And that's definitely a tricky one. Okay. And then for our final answer, for most scientifically productive astronomical observing site on the planet, our answer is Mauna Kea, Hawaii, which is 80%. Yes, and 20% is with our sister selected our sister telescope down in Chile. So we got a good spread here at Gemini. All right, excellent.
And just one thing to mention that was briefly mentioned earlier is that the Rubin Observatory, which is doing the legacy survey of space and time, this is they have the world's largest camera down there, and they're going to be taking pictures of the night sky every 2 to 3 days. So the entire night sky every 2 to 3 days, and they're going to be building up over time very, very deep images. It's in the southern hemisphere, so they can only see roughly 70% of the sky and not some of the stuff that we can see up here. But they're going to be building up deeper and deeper images of that 70% of the sky. And it's going to have the effect of something similar to the Sloan Digital Sky Survey. They're going to go down to about 30th magnitude. So this is, even fainter than we can see. I mean, we can do it, but we have to spend a lot of time to do it. And they're going to be seeing a lot of they're going to be looking at a lot of time domain astronomy, which means things that go bump in the night, supernovae usually. So stars exploding. So they take an image of the night sky once every 3 days or so, 3 nights. And they do difference imaging, and they look at galaxies and they say, oh, something went bump there. Something went bump there. Oh, we see something exploded there. And then they ask other observatories like Gemini. Gemini is really good at this, to then take a follow-up spectrum or a follow-up image in a different set of filters, so different colors, to get more information on that object. And so it's very likely, if we were to ask this question again in 10 years from now, that the distribution, I think Maunakea would still win. I hope Maunakea would still win, but that the distribution would change quite a bit, because Rubin is really going to change the landscape for astronomy in general, for all astronomers.
One thing also important to note, though, is that Rubin, a lot of its detections is going to be a lot of like initial detections.
Mm-hmm.
So it's going to be Rubin will be a lot of the ones like spotting something first, and then a lot of follow-up observations are going to be landing more on other observatories. But as Brian was mentioning, no one's a silo in science. We're all working together. All the different organizations are working together. And that's often true in Hawaii. A lot of our people think like, oh, our observatories are competing with each other. It's like, oh, no, they're not at all, because one observatory will be able to do one thing a little bit better than the other one. And so they'll collaborate and work together and work for each other's strengths and on what science we're doing.
Yep. There's friendly competition, of course.
Friendly, yes.
But we all have our different visions of how the observatory runs, and we all have our different strengths and weaknesses, it's for sure. And so, like, I would use Gemini for certain aspects of my science, but I wouldn't dare use it for other aspects of my science. I would use Keck, or I would use like Gemini South this semester I used rather than Gemini North, because of where the location of the objects that I wanted to see were in the sky. They were much more easily visible from the south than in the north. So that's important.
Thanks.
Cool. Thank you guys for humoring us in our poll.
Yeah. We had a question. Oh.
Yeah. Shall we go to the questions in the chat?
Yes, definitely. So thank you all for your questions. And just for security purposes, all comments and questions come to me, and then I repost them so everyone can see them. So please continue doing that. And yes, I think we have a question from Alani about flats.
Yeah. Let me see if I can get something up.
This is really
And
cool.
as you were saying, Brian, yeah, exactly. As you were saying, this was happening just before we got started with the session, and so maybe Sunny can talk to us about that after you share with us what you're going to share, Brian.
Yeah. So let me share. Okay. So this is actually the screen that one of the screens that Mark and Sunny would be looking at. So this is just I'm doing a screen sharing kind of our infrastructure here. So this is some of the same software that Mark and Sunny are using for tonight to diagnose everything about the instruments, the telescopes, the data that's coming in. And so this image right here, this screen is called SegPlot. This is actually an image from last night. So this is something that Mark and Sunny observed about roughly this time last night, about 23 hours ago. And this was a standard star for a program that's looking at clumpy galaxies in the intermediate age universe, so when the universe is about half its current age. And so we take a series of calibrations for any observation that we take on the telescope. It depends on which type of light you're looking in and what the nature of that observation is. So if you're taking an image of the sky versus a spectrum, of a particular object, you'd have different calibrations associated with that. And what I mean by calibrations is removing the effects of the Earth, of the optics of the telescope, of the peculiarities of the instrument, anything terrestrial, of the detectors, things coming in from the outside, so cosmic rays, really high energy particles that are interfering with the detector, removing all that chaff, and just getting right down to the intrinsic properties of the source that you're interested in. So we want, we take an image. So for example, for anybody that wears glasses, so if you take your glasses off, the image is not corrected. That's why you're wearing glasses. And so when you put the glasses on, that corrects, that calcifies, that clarifies what you're seeing. So there's some sort of correction that needs to be made to the optics in your eyes that helps you see that object in front of you clearly. And so it's the same type of thing. So in this particular case, we're using what's called an integral field unit. And this is a combination of an imager and a spectrograph. And so a spectrograph, as we mentioned earlier, is something that disperses white light. In this case, it's infrared white light, disperses it into its constituent colors. And so it makes a rainbow effectively. Rainbows work by refraction. This one works by diffraction, but basically same principle-ish. And so it's dispersing the light into these bands here. Okay, and so this is an image. This is what's called a white light image from the integral field unit. This is or a reconstructed image. This is the star that we're looking at here on the left. And at each pixel, so this individual pixel, we actually have a spectrum of that source. So we make a rainbow out of each one of these pixels. And that's what's shown here. So each different spatial location, you can see different bands. This is in the upper left portion of our field of view. And so it represents here on our detector over on the right-hand side. I've actually shifted around the image a little bit, so there's not a one-to-one correspondence. And so this is not even the object of interest. This is not the galaxy that's far, far away. This is a star that's used to correct the absorption of the atmosphere. So it's called a telluric standard. And so it's correcting for getting this data allows you to correct for absorption of the light by the atmosphere by certain molecules. And so we take a spectrum or integral field unit spectrum of usually an A star. So usually something that's very easy to model that has nice features, hydrogen absorption features. And we say, okay, we know what that star should look like because we know the brightness and we know roughly what the spectral features should be. And we know what we've observed. And so if we divide those two things, then we can actually get what the absorption, the level of absorption, level of attenuation of the atmosphere of the photons coming from outside. And so that's a correction that we need to make. And then you can apply that directly to your science data. And there's lots of different considerations that go into this. So I'm kind of glossing over those. Of course, the atmosphere can change over time. Of course, where the spectrum is, if you look at a star that's variable brightness and you don't model it well, that could be a problem. The star can change locations over time. You could illuminate portion of your detector, and that detector could have less response, so it could respond less to light than other portions of the detector, and so you have to make a compensation for that. But this is a basic sort of correction that we do every hour to hour and a half throughout the night if we're looking in the near infrared. In the optical, the atmosphere is not as bad at absorbing light. There's just a few bands, like very small regions of wavelength that there's this telluric absorption. Otherwise, it's not really a problem. So this is more for the near infrared. And so then one of the things that we do after that, so I'm going to change nights. So I'm going to change to tonight. So this is right before our session. It was like frame 9 or something like that. So we actually took calibrations because the weather was very complicated last night. we weren't able to, normally we would take the calibrations right after taking the observations so that we're at the same location in the sky as the observation that we took. So there's something called flexure, which is due to gravity, which causes movement, apparent movement of these spectral lines, can be in kind of any direction, but normally left, right. And so this is dependent on the position of the telescope, both in terms of elevation and in terms of something called the cast rotator angle, so Cassegrain rotator angle. All of our instruments are housed in this instrument housing right here. So this particular instrument was Genius. And so this whole structure that contains the instruments rotates around as the night sky rotates around, and that can actually change the gravity vector for relative gravity vector for all of these instruments. And so what Mark and Sunny did earlier this evening was to go back. They basically simulated the observation again. So they went back to the location of where they observed it last night because our dome was closed and we had some time to do this. Went back to the same location, so same elevation. They actually rotated our entire instrument cage around so that we were in the effectively exact same location as where the target was observed. And then they took these other calibrators. So let's go back a little ways. Oh, nice. So the arc lamp turned on, looks like, Mark. So this is a flat here. And this is to measure the response of the all of the optics and the detector to light. And so we have a light source that so it's actually, so we have, this is a picture of our telescope, very crude picture of our telescope. We have the primary mirror here, and then we have our secondary mirror here. So light comes in from the top, hits the primary mirror, goes to the secondary mirror, goes through this hole in the primary mirror, which is the size of the secondary, and goes into this Cassegrain cage or instrument cage. Hits this tertiary mirror, which we call the science fold. And so if we were on sky, so if we were observing on sky, this tertiary mirror would actually have, if it was going to Genius, it would have about a 45-degree angle, and the light would be reflected right into Genius, and then there'd be all sorts of things that happen in Genius. And so we have this other part of the cast cage, so another component equipped in the cast cage called the Gemini calibration environment, or lovingly called GCal. And we have a bunch of lamps inside of there. And so these lamps can illuminate, and they illuminate in different wavelengths, some better than others. And so we have lamps that we use for optical, we have lamps that we use for infrared. Depending on the wavelength, we may change the exact set of lamps that are illuminated. And so here we just have a flat lamp. So we basically just turn on an infrared diffuser or a quartz halogen lamp, and we illuminate Genius. And in this case, the low resolution, what's called the low resolution IFU, so some subcomponent of Genius. And this is its response to light. And so you can see some features in here. So you can see some lines like this. This can be due to dead pixels on the detector. This can be due to readout problems. This can be due to, so these are dead pixels right up here. This is our bad pixel patch that we keep an eye on all the time. This is really important when we do something called cross disperse spectroscopy. And you can see actually that the response changes as a function. So this direction is wavelength. It's redder down here and bluer up here. So you can see that this is the scale bar right here. So purple means not illuminated so much. Yellow means really illuminated on this stretch. And so you can see that this is brighter than this part here. So the bluer part is less illuminated. The redder part is more illuminated. You can also see spatially. So remember, we're taking slices basically of an image. And so you can see spatially, there's something called vignetting. So there's a fall off of the illumination as you go further and further from the center of the IFU, the integral field unit. So that's this slit and this slit here. They receive about 30% of the light of the inner slits. And so we want to correct all of that because that's not real. That's just what we measure. And so we want to remove all of that in order to get to the intrinsic properties of the source we're looking at. And then the next thing that Mark and Sunny did was to take arc frames. And so these are, when you see a rainbow, you say, oh yeah, that's red, that's indigo, that's violet, no problem. But that, we're making a rainbow here, but it's a mathematical rainbow. We're breaking up this, the light, the white light, the white infrared light into thousands, tens of thousands, millions, billions sometimes of constituent colors. And so we have to assign numbers to each one of those colors. And so that number is the usually wavelength or frequency. And so we have a picture here. This is just a black and white picture. We colored it, but it's truly just black and white. It's ones and zeros effectively. And so we have a value and it says this, if you see down at the bottom right, it says value 37. So this particular location, we received 37 of something, right? And so we translate that into the number of photons that hit on the detector. And in this particular case, we know because we've illuminated an argon lamp. So we know argon, we know the element's emission features. So just like we saw absorption features from hydrogen at certain wavelengths, we know there's emission features of argon at certain wavelengths. We can match that up. We can say, that one right there at pixel location X 537.6 and Y 321.8. That corresponds to the wavelength, I'm just going to make something up, 1.123 microns. Say, okay, good. Okay, so I know what that is. So once I go and take my image or my IFU observation, this X and Y location exactly corresponds to that wavelength. And so if you see an emission feature, let's say from hydrogen, at that particular location, you say, that's hydrogen. And I know what hydrogen is in the laboratory on Earth. That's 0.65 microns. It's the H alpha feature. It's 0.65 microns. And I've measured it at 1.123 microns. Then that actually gives me a Doppler shift. So I can measure the Doppler shift of that light. And I can figure out, as Emily said earlier, so galaxies are receding from us. And they're receding roughly in direct proportion to how far away they are. So I can actually use that Doppler shift to measure how far away that particular galaxy is. And then there's all sorts of other wonderful things that I can measure about the properties of the galaxy. But only if I've done that proper calibration. If I've not done that proper calibration, then all this is for nothing. Or even worse, I get bad information and I think, that galaxy is this far away when it's really a lot closer. Not really a lot closer, but like incrementally closer or incrementally further away. And this can bias my view of those particular sets of galaxies and then bias my understanding of the properties of those galaxies.
Funny thing, while you're talking about flats, I was checking the Slack channel and 2 days ago, someone shared that they caught a satellite trail going straight through one of the flats.
Yeah.
Yeah.
Yep.
Mhm.
Yep. Yeah. So that's we take something called twilight flats. So this is another set of observations that we do, and this is done. We're starting to do it in the evening here, but mostly in the morning, when the sky is thermally very quiet and has settled down a little bit. And so we take imaging twilight flats just to more or less see the response of the detector, to remove the night sky. And it so happens at right around sunset and sunrise, there's a lot of satellites running around. And you can see them naked eye a lot of times, but you can also see them in little tiny pinhole images like this. And so we actually just go to what we think a blank portion of the sky is, and we just start kind of like randomly moving around, and then we'll median all of those and create like a basic response of the instrument and the optics to the night sky at that particular wavelength. But sometimes the night sky, or what you think was empty, it's not so empty.
Yeah.
So there's always things that we have to calibrate out, and unfortunately more and more satellites these days that we have to deal with and calibrate out.
That was a brilliant explanation. Thank you so much. And Brian and Emily, and I'd like to invite Sunny if you would like to add anything else about doing calibrations, please do. And the question, just to remind you, was what kind of flats do you do to take calibrations, and do you do any of the image processing during the night, during the day, or is that sent to the scientists? So Brian pretty
I
much
didn't answer
answered
like half of the
all of those
question.
questions. But please, Sunny, do you have anything else you'd like to add?
Yeah, primarily from my side, the flats are, I think of GMOS, which is our imaging instrument. And like Brian was saying, we take those in the twilights, usually in the mornings. And as my job description is science operations specialist, and our working group actually processes those flats, depending on how frequently we can take them, but usually about once a month, sometimes every couple of weeks. And those get uploaded in our big archive of data, and then astronomers and even people like you can go to our archive and download all of that data and the calibration data and start doing your own data processing and research. So that's, I do want to mention, since conditions have improved a little bit, we're going to try and open up here. And in just a couple of minutes, we're going to slew the telescope to a tuning star, which kind of calibrations is an important part of getting the shape of our mirror calibrated for the night sky. So we look at a bright star and we know what it should look like in a telescope due to mathematics and physics experiments. And so we'll see what it really looks like, and then using a very fast changing mirror called a deformable mirror will actually change the shape of the star and use that to make what we see match what it should. And once they match, that means that our mirror is the right shape. We'll use that for the rest of the night. I don't want to necessarily spend too much on the technicals unless someone really wants to know. But anyway, that's what we're doing here. Maybe if you want to just listen in for a few minutes as we set that up, that's up to you. But that's what's happening here.
That would be great. Yeah, and I'm VNCing, Mark. I'm VNCing into your screen 5, I think, not interactive. So I'll just follow along. I think you'll probably GAC. Will you GAC it? No, maybe you won't actually, right? For the tuning star.
I won't. No.
Do you have a quick lookup? Maybe 6. Yeah, you have it on 6. So maybe we'll be able to see like AtCam and all this kind of stuff. So I'll bring that up as soon as you guys get going. So maybe we can I think there's a couple other questions. Yeah.
There are another one from Aman on how do you detect dark matter and dark energy in the night sky? Is that something that Gemini can do?
Okay, these are good questions, long answers.
Yeah.
I'll just give a couple of examples. So for dark matter, dark matter and dark matter energy are very different things. Dark matter interacts gravitationally. Dark energy, as far as we know, it's kind of the opposite of gravity. So it expands things, pushes things apart. And it's this is debatable, but it's increasing in potency over time. And so dark matter is for gravitational purposes interacts like normal matter. And dark energy is a vacuum energy that we don't really understand dark matter either. But dark energy is a vacuum energy that's pressure that's pushing everything out. So one collapses things, the other one expands things. Just basically. So dark matter, there's a variety of different ways of trying to detect dark matter indirectly. Most effectively every single experiment in the sky is indirect detection. One is this is how it was kind of first theorized, is the rotation curves of galaxies. So Emily showed the Milky Way, and the Milky Way rotates. And if we just considered the matter that's the flour in the pancake, so just the stars and the gas in the pancake there, what should happen is that we see stars moving around the central region of the galaxy, and then as you move further and further out, rotation should increase, so the faster velocity. And then at some point it should decrease because you start to run out of matter. But what we actually see is that it increases or plateaus at high radius. So this is what's called in the halo of the Milky Way, which is the term that we used earlier. And so there is necessarily some unseen component of matter. So it's not the gas, it's not the dust, it's not the stars, it's something else. And so this was theorized to be dark matter. We have no idea what, like God of the gaps kind of thing that we don't know. So there's something out there that seems to be gravitationally interacting. And so there's all sorts of candidates for this, that it's, you know, just failed stars or more exotic particles. We don't know, but that's one of the ways that we can see it.
Yeah, dark
Indirectly.
matter is so it's excess gravity that we cannot account for.
Yep.
And the reason why we can't account for it is it's likely something that's not making light. And so an optical observatory like Gemini has difficulty seeing things that don't make light because we use light to see with the observatory itself. So an optical observatory like Gemini would be used for detecting essentially the effects of dark matter on something. And so usually where we're seeing effects of dark matter is on galactic scales. So inside other galaxies or within the Milky Way galaxy.
Flew in there now.
Oh, nice.
Okay.
Are you able to?
Yeah, so the telescope is moving now. So let's see. Yeah. So I'll just share the screen. Okay, so this is the thing that we saw earlier. This is the telescope status display. You can see a bunch of things moving right now. This is real time, so this is actually this picture is a bird's eye view of our dome structure. You can see our shutter here in the black. That's a representation of the shutter. Our primary mirror is represented by this white circle here. So you can see that the shutter is the dome structure is turning around, that the primary mirror is moving. So the telescope has reached its elevation and it's now mostly just swiveling around. Everything is swiveling around. You can see our tertiary mirror was moving. So just what I said earlier, it's at a 45-degree angle. So we have light coming in, or will come in up here, hit the primary, hit the secondary, go into the gas cage, then reflect into G-nears. And all these measurements here are locations in the night sky that we're trying to get to. So this right ascension and declination, this is how we measure coordinates on the night sky. And so as soon as we get there, I'll shift to a different screen and we'll actually see that the star in the acquisition camera that will be used for tuning the optics for tonight. So in the meantime, we can just really quickly talk about, so that's dark matter. Another like really popular way that for astronomers to see the effects of dark matter is through gravitational lensing. And this is something that almost everybody is familiar with because the first image from the James Webb Space Telescope that Biden released, I don't know, about 3 years ago, roughly. I don't know, I can't remember. Time doesn't mean anything anymore. But this S-Max cluster with all these like little squiggly things in the image that don't look really like normal galaxies, and those are actually lensed light from the background. So these are very, very distant galaxies that have been gravitationally lensed. So the gravity has basically acted to focus that light. So you have a telescope that you're looking at this, in this case, the James Webb Space Telescope, you're looking at this cluster of galaxies, this very massive system of galaxies. And all that mass is additionally acting as a telescope to focus the light from the background. And so you can actually calculate based off of how much lensing occurs, you can actually calculate the mass of that entire system. And if you add up all the gas and all the stars and all the dust in those systems, it doesn't even come close to the amount of mass that needs to be there to do that type of lensing. And so it's only about 10 to 20% of the entire mass. And so that tells you that there is definitely an unseen component of matter there. And so what that is, we don't know. These are all indirect. Dark energy, we measure by basically, there's a variety of different ways of doing it, but the expansion of the universe. One of the things that we use for this is what's called standard candle in astronomy. So it's something that of known brightness, of known intrinsic brightness, One really famous one is a type 1A supernova. So this is a white dwarf, a stellar remnant that is accreting matter, usually from a stellar companion. So it's you can think of it as a core of a star held together by electron degeneracy pressure. And another star is dumping matter on top of it. And there's a certain limit, mass limit, above which electron degeneracy pressure, this pressure of quantum mechanics, cannot maintain the structure of that stellar remnant. And so that is 1.4 solar masses, 1.4 times or 40% more massive than the sun. This is something called the Chandrasekhar limit.
Okay, can you take a pause and just
Yep.
can you walk us through the light path of the telescope,
Sure.
since there's some interesting stuff that our light's doing in our telescope
Sure.
right now,
Yeah.
and just explain what the light path of what we're looking at
Yeah.
here on the screen.
So this is probably our most complicated light path. So this is again, we have our science fold in, but we also have something called the adaptive optics fold in. And so we are using a dichroic to give, so this breaks up the light.
Maybe start back a little bit farther. So
Yeah.
where's the top of the telescope in that diagram? Where's our primary mirror, secondary mirror, and where everything's going?
So light is coming in from our star. So let me switch over to the screen where the star is. Okay, so this is the star. This is the tuning star, and this is the acquisition camera. And so the Sunny is centering it up right now, and then he's gonna pipe the light through, and then we're gonna start making some measurements. So this is a real star on sky. And so the light. Yeah. Okay, so the light is coming from the star up here. It's hitting our primary mirror down here, this big green thing, hitting the secondary mirror, going into the cascade, and then all this stuff happening right here. So this is the acquisition camera, AC there. And so there is light going to optical light that's going to our AO portion of our telescope. So that has this deformable mirror inside that makes corrections. And
AO is adaptive optics, and the adaptive optics system will subtract out the effects of the atmosphere on the area that we're making an observation. So right now we're calibrating it, but
exactly,
yes.
yeah. So we take a picture of the star, and we see it looks a little bit cruddy. It's not, like it doesn't look as good as we would like. And so, as Sunny mentioned, there are various corrections. There's actuators like pistons that deform mirrors, and that's our primary mirror. That can be our secondary mirror. That can actually be our AO fold that deforms in real time up to 1,000 times per second to make corrections for the atmosphere. And what we're getting right now is a measurement of what is the best engineering setup for us for tonight. Given the conditions. And so this can change based off of the temperature. So even the differential in temperature between the primary mirror and the ambient temperature, a variety of other factors. And so we're getting initial measurements on that, and we're trying to get the star as tight as possible in terms of the spatial profile. And so just make it as small as possible, because all of this, light that we're taking from distant galaxies and from close by things, we want to get it all focused into a single point so that we can, get as many photons as possible right into our instrument and make those measurements.
Nice. So that light path, so it's passing it through the adaptive optics system and then going to us to be monitoring that. Can we track the progress on with the other screen that you showed of getting that star into a point?
Let's see. So we actually don't take images. So normally we would be taking images. Right now, GNears doesn't have the ability to take those images at nighttime due to the fact that we're in a different camera mode. So we have effectively 4 different cameras on GNears. And so normally we'd be taking pictures, but the camera that we have currently installed is too coarse to take those pictures. So that's all going to be done like kind of on an engineering level. So we won't actually be able to see the effects of that. It's just that trust us, there's something going on in the background here that's making corrections to the primary mirror. So that's what Sunny's doing, and probably Mark's looking at, so as soon as we get calibrated, what are we going to move on to? what are we going to move on to next? So telescope looks good, sky looks good, all of our systems are in place. And so what is the science that we're going to go to next? I actually don't know what that looks like.
Brian, before we maybe address another question, I'd love to stay here for just a moment because Sunny is finishing what he's doing, and you said Mark is now deciding what is actually going to be observed. Can you talk to us about the different bands in which people submit, have their programs in, and poor weather bands, and what kinds of thoughts Mark may be thinking right now as he goes through that process of making a choice?
Yeah, sure. I'm happy to. And I would defer to Mark, but this is something that all scientists, staff scientists go through either on the day planning side. So we have something called a Q coordinator that makes a variety of different plans during the day. And so we don't know, we might have a reasonable idea, but we don't know going into the night what the conditions are going to be like. So the Q coordinator has this very demanding job of creating roughly 10 different plans during the day out of this gigantic pool of observations that are available, and saying, for this level of atmospheric turbulence, for this level of cloud cover, for this level of water vapor in the atmosphere, for this level of brightness of the moon, or whatever, here's what we can observe. And they say, okay, great. So I've filled out the whole entire night for that particular set of conditions. Okay, now I'll do it again. Now I'll do it again for a different set of conditions. And so Mark has a huge number of observations to pull from, plans, basically, roughly 10 on a given night. And then he matches up. So one of Mark's big jobs is to assess the conditions at that time. And also, like, as Sunny said, there's sucker holes and all these kind of things. There's Maunakea can trick you all the time. And so not only what the conditions are now, but what are they going to be when you start to make that observation? Is that observation going to be worth it? Like, how long do you need to spend on that observation to make it scientifically productive? And so if you think, well, these conditions will probably hold for another 30 minutes or 45 minutes, then I'll go ahead and trust the conditions that I'm measuring now, versus actually probably things are going to degrade, or we see clouds coming in on the satellite, or things are just too volatile in terms of the twinkling of the stars, so the turbulence on the ground and in the atmosphere. And so I'm going to actually be more conservative, and I'm going to go to a less demanding plan. And so all of our scientific programs are matched up to a certain type of set of conditions. And so Mark's job in large part is to juggle all of these different things. And so, as Jamika mentioned, we have different bands. So band 1 is the highest priority set of observations. And usually, and not always, but usually those have the most demanding set of conditions. So photometric, meaning no clouds, what we call IQ 70, which means that it's the 70th percentile or better, seeing, so this is the amount of turbulence. And so band 1 programs demand those types of good conditions. And then we have all the way from band 1 to band 4. Band 4 is technically considered weather loss, but we actually do a ton of great science on band 4. And band 4 is usually used for, oh, it's super cloudy. Oh, there's, it's really, really bright out, plus clouds. It's, the atmosphere is super turbulent, plus there's a little bit of clouds. But these programs are designed to utilize those conditions effectively. And so Mark is probably, well, Mark, what's your calculus like right now? I see the satellite is not definitive on what's going to happen.
Yeah, so we're just we've had a little bit of a delay. Some of our Altair is requiring that we do some restarts. So
okay.
yeah, we're still thinking on this. Yeah.
Okay. So yeah, this is how every night goes. You have your plan, and then something knocks you down, and then you have plan B, and then something knocks you down again, and then you have plan C. And so it's important. There's, Mark and Sunny are in the control room tonight. They'll be there likely till the end of the night, and intrepid observers, and they got to stay awake and stay vigilant all night long. But what you don't see is that there are hundreds of people that actually get everything ready for Mark and Sunny to be, ready to utilize that time, hit the ground running and utilize that time as much as possible. And as Sunny mentioned earlier, if things start going wrong and, Sunny's the first line of defense, sometimes as staff scientists, we are also able to help a little tiny bit. Our technical knowledge is not as much as the SOS's. But first line of defense is the night crew. And then we have people on call, whether it be the Q coordinator or the manager of the telescope or technical staff, that if we have an issue, like for example, they're having an issue with Altair right now, that we can rely on expertise for people that are, really know these instruments like the back of their hand.
Thank you, Mark. Thank you, Brian, Sunny, for getting us up to speed on what's happening and the action that's happening right behind me in the control room. Okay, wow. We have about 9 minutes left, and I think maybe
So a lot of the things we want to do. Yeah.
It was good conversation.
Yeah, it's great. I'll just
It
come
has
back
been.
to the
It has
dark
been.
energy thing really quick. I'll just finish up that answer because we're almost to the end of it. So as I was mentioning earlier, we have standard candles in astronomy. These are things of like known brightness, intrinsic brightness. And so they allow us to measure the distances to things. So if we know the brightness and we, the intrinsic brightness, and we also know the apparent brightness, so we see it in the sky, then we can understand the distance, because light just goes as r squared. And so so this Chandrasekhar limit for type 1a supernovae, when the mass exceeds this white dwarf mass exceeds this limit, these stellar remnants explode in an event called a type 1a supernova. And that, there's considerations associated with the chemical composition of that white dwarf or the amount of dust that's in front of the white dwarf. But basically, you can count on it being some number of units of brightness. And then you observe it and you say, okay, well, it's this bright according to my telescope, and so I know that it's then this far away based off of the recession properties of galaxies. So these are stars that blow up in other galaxies, and they're as bright as the entire galaxy for a short period of time, as bright as the entire galaxy itself. And so you can do this over and over and over and over and over again, and you can kind of map out the recession velocities of the universe, right?
Yeah.
And so then you can see, not only is everything expanding away from us, nearly everything expanding away from us, but it's accelerating. And so if it's accelerating, that's weird, because if you have just gravity, things should be like, either contracting together again or at least slowing down. But in fact, it's accelerating. And so that's weird, and that shouldn't happen. And so this requires another presence in the universe. And this is what we call dark energy. And currently it makes up 73% of the matter energy density of the universe.
Yeah. And one thing in terms of dark matter and dark energy, they're both called dark just because they're largely mysterious, but also because especially when it comes to dark matter, this is something that clearly is like has mass, has gravity within the universe, but we are not able to detect it. But a good portion of the reason why we cannot detect it is up until very, very recently, everything that we've understood about the universe in terms of astronomy comes from the study of light. And if something is not making light, then we're not going to be able to detect it. And we can just study a lot of stuff with light. Heat is a form of light, that's a form of infrared light, but things need to be making light for us to see it. Now, I say that like up till now, because in the past decade, we have began to just detect gravitational waves, and gravitational waves are not connected to light. They're not made by light. An event that causes a gravitational wave event can also cause light as well. But by detecting gravitational waves, we are starting to calibrate something in astronomy that will be able to study the universe that is not dependent on light. So that might be the breakthrough of figuring out what dark matter is, what dark energy is. Right now, a lot of our For dark matter, Brian mentioned there's a few theories of what dark matter is. What is this excess gravity around galaxies? My computer just shut down, but you can still hear me. Okay. But what dark matter is around galaxies. The funny story with it is the first people who wanted to come up with a theory for dark matter was particle physicists. And particle physicists went, okay, well, we think that dark matter could be weakly interacting massive particles. That's a particle that's big for being a particle, but it doesn't interact with a lot of things around it. Therefore, it's not making light. And so weakly interactive massive particles, their acronym becomes WIMP. And so, but for the particle physicists, in order to try to determine if there's WIMPs, they needed to go to CERN. They needed to play with their Large Hadron Collider for a bit in order to detect a possibility of WIMPs. And they did detect some WIMPs, and some dark matter has been contributed to WIMPs, but they were actually taking such a long time that astronomers came around and they were all impatient and said, like, oh, you know, we don't want to wait for those
As we are.
Yeah,
as
we don't
are.
we don't want to wait for the particle physicists and their WIMPs anymore. We want to come up with our own theory. And their theory, the astronomer theory, is massive compact halo objects. So those are objects, think planet, think Jupiter, not big enough to be making light, hanging out in the halo region of a galaxy where it's very less likely that they're going to interact with stuff. And so it'd be very, very difficult for us to detect because they're not making light and they're not interacting with things that are making light. And then astronomers love coming up with weird acronyms. So massive compact halo objects became MACHOs. So the two leading theories for dark matter for a good period of time were WIMPs and MACHOs. Whereas MACHOs actually has really been dying down as a theory. WIMPs are a little bit more popular, but even with how much we're detecting on either of those, it's not accounting for the amount of dark matter that's within the universe. Now, as far as astronomy, like oftentimes a lot of these things we're detecting the effects of dark matter or the effects of dark energy, but we're not really detecting what they are. We're not great on that side. A lot of people at CERN, a lot of people with particle physics, a lot of theorists are the ones really diving into what are these things. And that's something that we're working on solving. And actually with that note as well, I saw in the chat before my computer died, there's a question relating to could our telescope create a 3D timeline map of the entire universe from past to present? And one telescope alone would not be able to do that. One telescope could definitely contribute to a project like that, but it would take a lot of science and a lot of things from optical telescopes to submillimeter telescopes to radio telescopes to the Large Hadron Collider at CERN to gravitational wave detectors and all of that data working together in order to create a comprehensive timeline like that.
Perfect. Thank you so much, Emily, Brian. And I see we're getting some answers to other questions in the chat too from Annalise and a few other questions from Aman. There is one question here on black holes from Aman. How do you find black holes in the night sky? Is that a capability that Gemini has?
It's absolutely a capability that Gemini has. So there's a lot of different ways to find black holes. They're black, so you might think that they don't emit radiation, and they don't. Inside their event horizon, but outside their event horizon, where light can escape, they have accretion disks. So this is where they accrete matter around them, that eventually usually goes inside the black hole, and it heats up gravitationally and through friction. It gets really, really hot, and it emits high energy photons. And so we talked about optical light, we talked about infrared light. Infrared light is actually less energetic than optical light. So if you go more energetic than optical light, you get to the ultraviolet, that causes sunburns. And then even more energetic than that is X-rays or gamma rays. And so one way to see black holes, active black holes, is through X-ray telescopes. And so the Chandra Observatory or XMM Newton, ROSAT was a famous one a while back. This is one way to see the shining of the accretion disk, the high energy photons that are coming of the black holes. And so this is a lot of people have found black holes based off of X-ray observatories, and then we follow them up with optical or near-infrared telescopes to determine, for example, the kinematics or the motion of the gas around those black holes. And you can actually, so the argument that I made earlier is that the rotation of the galaxy had something to do with the amount of mass that was present there. Same thing, same. You have rotation of the gas around the black hole. You can use physics to determine the mass of the black hole, even though you can't really see directly the black hole. But if we want to discover them just from Gemini alone, actually we can see those high energy photons in a spectrum. So the spectrum that I was showing earlier, that was of a star. But if you take that same spectrum of a galaxy, you'll see emission features. So you'll see from hydrogen, for example, or from doubly ionized oxygen, or from nitrogen or sulfur, or all sorts of neon, all these different elements. And so you can actually work out based on the relative strengths of these different emission features, what type of photons are being emitted by the source in the galaxy, the dominant source in the galaxy. And so if you see like a lot of very high ionization features, so meaning that like oxygen is doubly ionized or neon is quintuply ionized, these are telltale signs that there's very high energy photons present ambient in the galaxy. And so there's only a few processes within a galaxy that can cause the emission of those type of photons. That can be very, very massive stars that are very bright, very hot, and black holes. And so you can actually work out mathematically the chance that there's a black hole in that galaxy, and based on certain ratios of certain emission lines, that you can basically say with 100% certainty, yes, there's a black hole in that galaxy. And then you can use those emission lines to tell how much matter it's accreting, how massive the black hole is. We had a staff scientist here that worked with quite a few of us that discovered one of the most accreting black holes for its mass in the early universe with the James Webb Space Telescope. And part of the observations that gave rise to that James Webb observation came from ground-based observatories in the optical and the near-infrared. So we basically selected, say, oh, we don't see a whole lot in the optical near-infrared, but we do see a lot in the X-ray. And so that means that there's something enshrouded there. There's a lot of gas and dust probably accreting onto a central source like the black hole. And so this is Hye-Won Suh, and she just wrote a paper for the Nature journal presenting the discovery of that black hole. You can actually link it in.
Wow, that's fantastic. That you said that was Hye-Won?
That was Hye-Won, yeah.
Ah, congratulations, Hye-Won.
Yeah, there's now like press all over the world about this source. So if you look up, I think this is the wonderful name of the source, LID-568. Very famous LID-568 source.
We have a Gemini press release on that one
Do we?
too. Yeah, I think pretty sure we do. Did that come out back in November?
Sounds about right. Yeah.
Yeah. So yeah, we have the Gemini press release for.
I should stop sharing my screen.
Oh, yeah.
Right. Oh, here it is. Yeah.
So if you're watching my screen, we're about to close the loops and the star will start to look pretty.
Oh, let's go
Perfect.
take a look
Okay.
at that.
I just
Yes.
put the Gemini press release in the chat. Let me go to settings. So LD2. Which screen, Sunny?
This is 0, 1, 2, 3, 5.
And we've got a share screen. All right. Oh, look at that.
Sunny, do you mind just walking us through?
In the sky, yeah. And now takes a second for the loops to close. And there it is. Now the telescope sees it very steady. But we still have some clouds, so I'm going to get some more light here. Make some changes.
So right now you're basically just locking in on that star, right? You're trying to use it as a guide star.
Yeah. Yeah, we're tuning, but we got some clouds, so I got to make sure I have enough counts for the instrument to see the folks, have enough light to do its measurements.
So on this particular, so this is a wavefront sensor. On this particular wavefront sensor, we have the options of reading 1,000 times per second, 500 times per second, all the way down to 100 times per second. And so, Sunny, what are you dropping them down to now?
We're down to 200 times a second.
So with less frequent sampling, that means we get more photons in a given sample. And so we want to make sure that we have enough photons that we can make the measurement properly to make the corrections. So if you're down in what we call the low signal to noise regime, you can get aberrant corrections, and that can really do some bad things for your optics. And so we want to make sure that star is nice and bright so that we can. Oh, it's kind of a bummer that you guys are opening up, you're tuning and we're ready to go, and then we have to end the session.
It's great ending on something that's like watching this get better and better as we go.
Yeah.
Definitely. I agree.
As you see disappear, that's the cloud.
Oh,
Yeah.
go away, cloud. Shoo, cloud, don't bother us.
That's what we're going. That's what we're doing here.
See,
If the clouds let us.
yeah, so I'm gonna go over to one other screen really quickly. Okay, going back almost where we started, Gemini North status. See, basically Mark and Sunny are looking up, so this is what they're seeing, clouds move in and out. But an actual measurement of this, and this is something Sunny's super familiar with. He does a lot of like cloud modeling and when are the clouds going to hit us and how thick are those clouds. We have an application that Sunny wrote that we use quite a bit. This graph right here is actually a measurement of the attenuation. This is from the Canada France Hawai'i telescopes. It's right next door to the Gemini North Telescope, walking distance on Maunakea. And these measurements are attenuation in terms of magnitudes from effectively where CFHT is pointing, Hawai'i telescope's pointing. So you can see this is a measurement over time right here. This is a little bit behind. No, it's 21:07. Okay, so about 9 o'clock at night. And you can see these measurements are about 1 magnitude of attenuation. So if 2.5 magnitudes is a factor of 10 in brightness, this is about a factor of 2.5 or so. So for every, if it was clear skies, we would see 2.5 photons. Now we're seeing 1. And so this is why Sunny has to decrease. But if I come back to Sunny's screen. Actually, looks like the cloud is passed. And it's a lot brighter now. So yay, sucker hole.
Perfect. That's wonderful. And we can end with a question here. What's the significance of that bright vertical line to the left of the star?
That is a defect of probably the electronics that control the actual detector, which is basically the same kind of thing that's in your smartphone that takes pictures. They're just CCD pixels